Hi folks, this is the walkthrough for exam number 2. What I have up so far is the exam here. I have my usual file over here that I'm going to use basically as scratch paper. I already have the Excel spreadsheet up that I need, and I have a second Excel spreadsheet available for me to do my analyses in. So with that up, let's get started. Notice that I have entered over here onto my scratch paper the recommendations that I had made in Piazza on what questions would be good ones to start with and what order to do the questions in. So I'm going to be following those guidelines. So I'm going to hit begin and get in. So we will go down to question 19 first. Question 19, we have an equilibrium. On a scratch piece of paper, write down the equilibrium constant expression for the following equilibrium. Identify the exponents for each component using a negative exponent to indicate that the species is in the denominator. An equilibrium constant, K, is going to equal a fraction where we have the products over the reactants. So let's look at our products. We have the concentration of Fe3+. We have the concentration of Cr3+. We have the concentration of H2O. Now, we do not include the H2O because it is a liquid and it is not a solute or a gas. We raise these to the powers of their stoichiometric coefficients, 2 and 6. We're done with the product side. We now do the reactant side. So we have the concentration of Fe2+. We have the concentration of H+. And we have the concentration of Cr2O7 with a 2- charge. We now need to have our stoichiometric coefficients as our exponents. This is going to be to the 6th. The H+ is going to be to the 14th. And the dichromate is going to be to the 1st. Okay, we now have our equilibrium constant expression. Now notice that the instructions say to use a negative exponent to indicate that the species is in the denominator. So that's consistent with how the math works. So what I'm going to do is take this and I'm going to make the species that are in the denominator negative, indicating that they are in fact in the denominator. So this right here is our answer. This is simply the way that we can most easily enter that into this expression. So Fe2+ is a 6-, excuse me, yeah, H+ is a -14. Cr2O7 is a -1. Fe3+ is a 6. Cr3+ is a 2, and H2O is a 0 because it doesn't factor in. All right, question 10. The equilibrium constant for the reaction in the previous question is this. And we've given initial conditions, and we want to know what the equilibrium concentration is. This suggests that we need an ice table. This is the reaction we want. 1, 2, 3, 4, 5, 6 components. So I am going to put a table in here. Obviously, in a piece of paper, on a scratch sheet of paper, it's going to be easier for you. So I'm going to do 8 columns, and I'm going to do 5 rows, and you'll see why I'm doing that in a moment. So I'm going to put the species across. Okay, and there are 6 of these. There are, oops, I'm not doing this right. This is a product, of which we have 3. This is a product. We have 2 of those. We also have the 7H2O, but we don't care about that. I'm going to put my equilibrium expression there. Here we need the Fe2 plus, and there are 6 of those. We need our H plus, and there are 14 of those. And we need our dichromate. There's only 1 of those. Our initial conditions are, the initial condition of H plus is 1.00 molar. Initial condition of this, 0.0100 molar, and dichromate, 0.01100, and all other initial concentrations are 0. Okay. Now, if we look at our equilibrium constant, it is absolutely enormous. So what that means is that we need to start by shifting the reaction as far towards products as it is possible. So we have a shifted initial set of conditions. We will then have a change, and we will then have the equilibrium down here. So the next question is, which of these components is going to be our limiting reagent as we shift as far to the right as possible? Well, we use more H plus than anything else, but we have 100 times as much H plus as anything else, so that's not going to be the thing that runs out first. The iron 2 and the chromate we have equal amounts of, but we use up the iron at 6 times the rate. So this is going to be the one we're going to run out of first, and so we're going to have 0 of this once we have shifted it. So now how much did we shift by? Well, if 0.0100 was how much it shifted over here, 1/6 of that will be how much of the dichromate will shift. And so we find that our dichromate is going to be 0.0100 minus 0.0016667, extra 6 in there. We see what that is, and we have 0.0083, and that's the right number of sig figs for this. Now that we have this, we can because this is how much of something with a stoichiometric coefficient of 1 is, that will tell us what to do with everything else. We have 14 times as much of that of the H plus that goes away, so 14 times 0.0016667. We have that much, and we want 1.00 minus 0.023, 0.977. 0.977. Okay, I'm going to get rid of these to clear some space. We now need to know the iron and the chromium on the right-hand side. The iron is going to be the same as the iron on this side, so that's going to be 0.0100. This is now going to be twice this number, so we have 0.0016667 times 2 gives us 0.00333. All right. So we now have our shifted initial conditions. But we know that this has overshot a little bit because we're not going to end up with 0 of the iron. So the reaction is going to be shifting during the change line slightly back to the left. So since this one has a stoichiometric coefficient of 1, this one is going to shift by x. This one is going to shift by 14x. This one is going to shift by 6x. This one is going to shift by minus 6x. And this is going to shift by minus 2x. At this point now, we can add these columns to find our equilibrium position. 6x, 0.977 plus 14x, 0.0083 plus x, 0.0100 minus 6x, 0.00333 minus 2x. Clearing some workspace. We expect that we are we started out very, very close to equilibrium after we shifted it because of just how enormous this equilibrium constant is. So we suspect that when we have a certain number of x's that are being added to or subtracted from a concentration, we can probably ignore those. So the only place our x's are going to stay is here where they're by themselves. What we do now is we take our equilibrium constant expression, we take our equilibrium constant itself, 8.9 times 10 to the 56th, and we plug in our values for these concentrations. So this, the Fe3 plus, is going to be 0.0100 raised to the 6th power. We have the Cr3 plus, which is going to be 0.00333 squared. We have the Fe2 plus, which is going to be our 6x. We have our H plus, which is going to be 0.977. And we have our chromate, which is going to be 0.0083. Okay, now we want to solve this equation for x. So let's start by taking this out of the exponent. So we now have 6 to the 6th. This is now x to the 6th. And let's now multiply through by x to the 6th. And we will divide through by 8.9 times 10 to the 56th. We now have an expression on the right-hand side. Now, what do we do to get rid of the 6th? Well, we need to take the 6th root, which is the same as raising something to the power of 1/6. And now, on the right-hand side, we just have numbers. So you can plug this into your calculator. If your particular calculator does not have the raised to the 1/6 power, or raised to an arbitrary power where you could put in 1/6, then you can take this over to Wolfram Alpha and do the calculation there if you like. If we do it here, we find that x is 1.88 times 10 to the minus 13. And we have to do the check at this point to determine whether or not the assumption we made that these x values were small compared to what we're adding or subtracting from is valid. And in fact, this is so small that yes, it is indeed. Now the question is asking us for the equilibrium concentration of Fe2 plus, which is this, which is 6x. So this is going to be 6 times 1.88292 times 10 to the negative 13. And we have 1.12 times 10 to the negative 12th. In scientific notation, your answer is going to be some number times 10 to the x. Some number times 10 to the x. Enter your value for x, minus 12. Okay, we have our answer. Next question is number 21. The reaction we just discussed is strongly exothermic. If we raise the temperature, what would happen to the concentration of Fe2 plus? So exothermic means that heat is produced in the reaction. So reactants, equilibrium, products. Exothermic means it produces heat, so we put heat on this side. So if we raise the temperature, we add heat, and the reaction shifts towards reactants. And so now we look up here, the Fe2 plus is on the reactant side, so the reactant concentration should increase. Okay. Question 22. The vapor pressure of a liquid can be expressed as an equilibrium, shown here for hexane. C6H14 liquid is in equilibrium with C6H14 gas, and we have a pressure-based equilibrium constant of 17.6 kilopascals. So given this, let's write down what our equilibrium constant expression is. It is going to be the partial pressure of the products, C6H14, it raised to the first power, divided by, well, we don't have anything on the left-hand side that's a gas, so That's it. The equilibrium constant is just the pressure of our compound, C6H14. If the illustrated volume, which contains only liquid and gaseous hexane, is compressed to half its original volume and the system is allowed to reestablish equilibrium at the same temperature, what can be said about the pressure of the system? Well, we know that its pressure initially is 17.6 kilopascals. We then compress it and then allow it to reestablish equilibrium at the same temperature. Well, at that same temperature, the equilibrium constant is still just the pressure of hexane, and the equilibrium constant has the same value, 17.6, so the answer is that the pressure will be 17.6 kilopascals. This may seem counterintuitive because we compressed it. Shouldn't the pressure be going up? Well, no, because by allowing it to re-establish equilibrium, we are allowing some of the gas to condense. And because of the way the equilibrium constant is structured, where it is just the pressure of the one gaseous component, that equilibrium position will be such that the pressure in the container will be constant. This is why we can list a vapor pressure for a liquid, for any liquid, at a given temperature without having to specify anything about the volume that gas is taking up. Question 23, two simultaneous equilibria. We have AB in equilibrium with A separated from B. We have AC in equilibria with A separated from C. Here, AC is the solvent that all the other species are dissolved in. The system starts at a simultaneous equilibrium, and so we perturb the system from equilibrium by adding more AB to the sample. What happens to the other concentrations? Well, we add AB. That means that A is going to go up and B is going to go up because the equilibrium will shift to the right. Now, if A has gone up because of the first equilibrium, that means that the second equilibrium is going to shift to the left, and so C will decrease. Now, what is happening to AC? We could make an argument that the AC concentration increases. We could, because we are making more of the AC. That is also a negligible amount, so we could make the argument that the AC remains unchanged. So I do not remember exactly how this particular question is graded currently, but I'm going to go back into it and ensure that both of those answers, where you select this one or you select this one, will be counted as correct. We are now done with questions 19 to 23. We're now going to go up to questions 6 through 13 and go through the mechanism questions. All right, we have a mechanism. Notice that step 1 is the reverse of step 5 and step 4 is the reverse of step 2. M means any gas species, and we want the rate laws for each of these steps. So let's just write those rate laws. R1 equals K1 times concentration of Br2 times concentration of M. R2 equals K2 concentration of Br times concentration of H2. R3 equals K3, concentration of H, concentration of Br2. R4 equals K4, concentration of H, concentration of HBr. R5, K5, concentration of Br squared, concentration of M. So, how do we put that in? What it's asking for is the orders for each of the steps with respect to the various components. So for reaction 1, we have first order in Br2 and M, and 0th order in everything else because they don't factor into the expression at all. For step 2, Br and H2 are 1s. Everything else is a 0. Step 3, H and Br2 are 1s, and everything else is a 0. Step 4, H and HBr are 1s. Everything else is a 0. Step 5, Br is to the second power, and M is to the first power, and everything else is a 0. Okay. Which species in this mechanism are intermediates? Select all that apply. So in order to figure that out, we need to know about the overall reaction. Back up in question 1, we are told that the overall reaction is Br2 plus H2 yields 2 HBr. So the candidates for intermediates are Br, H, and M, because those are the species that do not appear in the overall reaction. If we look at the form of the mechanism right here, we see that the only place M appears, it is both a reactant and a product. It's a reactant and a product. So M is going to be a catalyst. Br and H, however, Br is formed and Br is removed. H is formed and then H is removed. So Br and H are our 2 intermediates. If you didn't get that correct, then a later question talking about the steady state approximation will have you specifically finding the steady state concentrations of Br and H. And as a result of that, should tell you that those were the 2 intermediates. Question 8. In the next few questions, we'll be analyzing the above mechanism using the pre-equilibrium approximation. On a piece of scratch paper, write the pre-equilibrium condition for steps 1 and 5. Remember that steps 1 and 5 were reverses of each other. And solve the result for the concentration of Br. The pre-equilibrium approximation says that in a reversible reaction, the forward rate equals the reverse rate. So that is R1 equals R5. That is the pre-equilibrium approximation. So we take our expression for R1 and we set it equal to our expression for R5. And now we are told to solve this for the concentration of Br. So copy that down. I'm going to isolate Br, divide both sides through by M, divide both sides through by K5, like so. We notice that the M's cancel. And now we need to take the square root in order to get Br by itself. So Br equals the square root of this thing. Well, we're trying to enter this expression in terms of exponents. So what is a square root? It is raising something to the 1/2 power. So this is going to be K1 to the 1/2. It's going to be K5 to the -1/2 because it's in the denominator, and it's going to be Br2 to the, to the 1/2. So K1 to the 1/2, K5 to the -1/2, Br2 to the 1/2, everything else is 0. Okay, got that one done. Question 9. If we apply the pre-equilibrium approximation to steps 2 and 4, what is the correct expression for the concentration of H? So again, we have R2 equals R4. So R2 is this. R4 is this. We are solving for the concentration of H. So divide through by concentration of HBr, divide through by K4, and putting this into the notation where we can easily see what the exponents are, we will bring this up here, raised to the -1 power. We will bring this up to the top, raised to the -1 power. And we now have what we need. K2 is going to be to the first, K4 is going to be to the -1, Br is going to be to the first, H2 is going to be to the first, and HBr is going to be to the -1. Everything else is going to be a 0. Done with that one. Question 10. Since HBr is the product of the reaction, we can consider the rate of reaction to be the rate of production of HBr divided by 2. Why do we need to divide by 2? Well, if we look at the overall reaction, we see that we have a stoichiometric coefficient here of 2. So the rate of reaction is going to be half the rate of production of HBr, because the stoichiometric coefficient of HBr in the overall reaction is 2. 11. Within the pre-equilibrium approximation, why can we ignore the production of HBr in step 2? Well, we have choices that the step is too slow to matter, except we haven't been told anything about how fast the reactions are yet. Because we already assumed that the rate of that step is equal to the rate of step 4, and they cancel out. And that makes quite some sense, because if we look at the mechanism, they are reverse reactions of each other. And in the pre-equilibrium approximation, we said that the forward reaction equals the reverse reaction. And so for all of the Br that is produced by K4, that same amount is being destroyed by K2. And so they cancel each other out. So that is the one that's going to work. We don't know if it's the rate determining step, and yes, we can in fact ignore it. Question 12. Within the pre-equilibrium approximation, what is the overall rate before we remove the intermediates? Okay, so the overall rate is going to be the production of HBr. So that is going to be step 3, because we've just determined we can ignore step 2, HBr, step 2 right there. And that's the only other step that makes the HBr. So it is going to be the rate of step 3, which is this one. Question 13. When you combine your answers to questions 8, 9, and 12, you should be able to get an expression for the overall rate of reaction within the pre-equilibrium approximation that excludes all intermediates. So if we take this expression here, our R overall equals K3, concentration of H, concentration of Br2. We now need to remove the intermediates. We know that H is one of them, so I'm going to plug that in here. And we have an expression somewhere, where'd it go? Here, for the concentration of H, which I will plug in for the concentration of H right here. All right. We have Br, so we need to include the concentration of Br right here, like so. And so let's see, we have 1, 2, 3, 4, 5, none of those combined because they're all different. We do have Br2 and Br2 here, so we can combine those to make it Br2 to the 3/2 right here. And we have our expression in a form that is actually very convenient for us as we are trying to put it into the Blackboard answer. So I'm simply shuffling the order of these so that they're in order and easy to see. So K1 should be to the 1/2. K2 should be to the 1. K3 should be to the 1. K4 should be to the -1. K5 should be to the -1/2. Br2 should be to the 3/2. H2 should be to the 1. HBr should be to the -1. Everything else is 0. We're done. Question 14. Oh, that's one of the ones we were supposed to skip, so we will come back to that. Question 15. We're going to use the same, analyze the same mechanism, but using the steady state approximation instead of the pre-equilibrium approximation. So we now want to construct an expression that correctly represents the steady state approximation for the concentration of H. So notice that this is in terms of the R1 through R5s. So we don't even at this point need to have these kinds of expressions here. So let's scroll back up to our mechanism and look at the steady state approximation for H. Here's our mechanism. So rate of production of H equals rate of destruction of H is the steady state approximation. So H is not involved in step 1. In step 2, it is produced. So on the produced side, we're going to have R2. It is destroyed in step 3. So on the destroyed side, we will say R3. It is destroyed in step 4, so plus R4 on the destroyed side. It is not involved in step 5. So we want R2 equals R3 plus R4. Now, there's a comment here, place the lowest numbered rate coefficient on the left-hand side. That's because we put R3 plus R4 over here and R2 over here, it won't get counted right. So we want R2 equals R3 plus R4. Save that answer. All right, question 16. Construct an expression that correctly represents the steady state approximation for the concentration of Br. So same thing as before. Steady state for Br up here. Our rate of production for Br is going to be 2 times R1 because you make 2 Brs there. We're going to have a destruction from K2, so that is going to be R2 on the destruction side. It is produced in K3, so we need to go back to the production side, plus R3. It is produced in R4, so plus R4 on the production side, and is destroyed in K5 twice, so plus 2 R5. Now R1 is the lowest, so that's the one that's going to go on the left. So we are looking for 2R1 plus R3 plus R4, 2R1 plus R3 plus R4, and we are looking for R2 plus 2R5, R2 plus 2R5. All right. Question 17 is one of the ones that we need to compare to the earlier stuff. So let's go back up and get started on these questions here. Now, for this, we need the spreadsheet. We are told in here that the password Arrhenius. So bring up the spreadsheet, password Arrhenius. So this shows up and these show up. So we now have what the overall reaction is, and we now have the species labels that we are trying to work with. Going back, we are also told that there are some conditions where the rate law is very close to this form we're used to, and there are some conditions where it is not. So the exam guides you to specific conditions where the exam law is well behaved, so don't veer too far from those specific conditions. The way to tell if it's a problem is if the simulation's not going out to very long times, meaning it's not coming down close to 0. I've also set up the spreadsheet so that the length of time is automatically the full simulation and the step size is automatically generating the full 2,000 data points. And for this exam, you should not have to modify those two parameters. So leave the times unchanged. Okay, start at 650. What I'm going to do is put that over here. Start at 650 degrees C, 0.00001, which is what we already have for the BR2. For the H2, 0.01. And the N2, we are putting at 1, and we're putting a 0 for the HBr. Okay. So that now generates our data. We are supposed to analyze the data we generate and identify which of these is correct. So copying our data the normal way, X comma Y, enter, Control C to copy, shifting to our new book, paste values. Now, we can tell right from here, that needs to go away. We can tell right from here that plotting concentration versus time is not a straight line. Therefore, we know it is not 0th order without even doing anything over here. We are now going to do natural log of concentration of A and 1 over concentration of A to see how these look. So equals natural log of that value equals 1 over that value. Oops, I always try to put in a parentheses there, and I shouldn't. Okay, we're going to take these, copy, arrow end down, over, shift, end up, paste. We are now going to try to plot this, end up, control click, control shift end down, scroll back to the top, insert, chart, scatter plot. So that looks a little bit curved, and you can see that even better if we have this only go up to about -10. That's got quite some curvature to it, so it doesn't appear to be simple first order. Okay, let's now do the same thing, looking at 1 over. Insert, chart, scatter. That one also is clearly not a straight line. So our answer is that under these conditions, the reaction does not appear to be a simple order in BR2. Now, why is this? This is because the concentration of both BR2 and H2 are changing in measurable ways over the course of the reaction. All right, let's see what we are told to do next. Using the method of initial rates, determine the reaction order of this reaction in BR2, H2, and N2. You will be modifying the initial conditions somewhat from the initial conditions specified in the first question. Part of the point of this analysis is for you to make decisions about what concentrations to use. When you are doing this analysis, you may notice that your first data point or the first few data points seem to sort of get going slowly. This is a result of the steps in the reaction mechanism needing a tiny bit of time to reach the pre-equilibrium or steady state conditions that make the overall reaction rate law well behaved. Start your initial rate analysis after those first few points. Okay, so what we have to do is start at these conditions. Okay, so our first set of concentrations are going to be this set that we were given specifically. So I'm going to come over to our new data here, and I am going to take our data, copy it. I'm going to make myself a new sheet to work in, and I'm going to give myself some space and copy those values in. And we are going to need a place to put an initial rate, and we're going to need a place to put the order of the reaction that we end up calculating. So let's now figure out our initial rate. So I'm going to select just a single page down's worth of data, and I'm going to put in a scatter chart. Now notice that the first few data points, it looks like it's sort of curving over a bit. That's what the instructions in the question were pointing out to you. So we want to skip those first few data points, and it looks pretty linear without too much noise, so I'm even going to take less data to make sure that we can avoid too much of the curvature. So I'm going to get rid of that chart. I'm going to go to about maybe the third or fourth data point, and I'm not going to go a full page down. I'm going to do something about like that. Insert, chart, scatter, trend line. Looks like a pretty good fit. Play a display equation on chart. Add some sig figs. And we have an initial rate of 0.000933. Okay. Don't need this chart anymore. Now need to generate some new data. Okay, coming back over here, we are now ready to double one of our concentrations. And so let's start with the BR2, double it there. We hit enter. We wait for Excel to catch up. We get our data, x comma y, copy, over to our new spreadsheet, paste numbers. Oh, this was plugged in incorrectly. That should have been a 1. We know that our new concentrations over here are where we have this doubled. Let's take a look at our data. I'll do a single page down just to look at it. We can still see the curvature up at the front. Otherwise, it's looking relatively straight. So I will do starting on the 3rd or 4th data point, and I will do a not full page down to find the region to plot. Let's find a trend line. Determine our equation. Add some sig figs. And we have 0.00137762. Okay. Now, using the formula that I talked about on Piazza, in the same post where I discussed the order in which you should think about doing these questions, we can find the order by taking the natural log of the ratio of the two rates, initial rates, divided by the natural log of the ratio of the concentrations that we're changing. And we find that our reaction order is 0.5 or 1/2. Okay, done with that one. Back here. We now want to change our second concentration to be double of what it was initially. We let Excel catch up, and we take our data, x comma y, copy, over to here, paste numbers. For reference, copy these over. That one's a 2. Take a look at the data, just a single page down across, just to take a look. Hard to tell given where the scale is, but what you could do is look at our scale, have it maybe start at 0.00006. Yeah, it's looking pretty straight again, except for that very first point. So I'm going to skip the first 2 points just to have some margin for error. Not a full page down. Insert our scatter chart. Trend line. Looks pretty good, although maybe a little bit of curvature on that. So maybe I went a little too far. So maybe we'll only go about that far. Insert, chart, scatter. Give us a trend line. Select it. Display equation on chart. Give ourselves some more sig figs. 0.001845. We're going to use our same formula for the reaction order. The ratio of the initial rates divided by the natural log of the ratio of the concentration that was changing. And we get very clearly first order in H2. We now are going to try N2. So our concentration, our initial concentrations here are going to be that. Come back over here, change that to a 1, and change that next one to a 2. Wait for Excel to catch up. X comma Y, copy. Don't need this anymore. Paste numeric. We have those up there. Insert scatter chart. Again, looks like only our first data point is an issue, so I'm going to skip 2 for a margin of error. 1, 2, start there, and go down just a few data points. Insert chart, trend line, equation on chart. Nope. Number, get some digits. 0.00091021. Now, our reaction order, same formula, natural log of that divided by that, divided by natural log of that divided by that. And we find something that is nearly zero. So our reaction order with respect to N2 is 0. Okay, one more to do. We need to do the HBr. So I'm going to put that back here. And the question tells us to set an initial concentration of HBr to 0.00001. That. Okay, wait for Excel to catch up. X comma Y, copy over here. Paste numeric. Nope. 0.000001. All right. Insert scatter chart. First data point looks bad. We'll skip 2 just to make sure. That should be far enough. Insert scatter chart. Trend line. Number. .123936665. All right. Finally, we need to double that one. So take this, change that to a 2. X comma Y, copy. Bring the data to the new spreadsheet here. Putting our conditions in so we can keep track of everything. 2. Yeah, first data point looks off, so as usual, we will skip an extra one just for safety. Insert chart, scatter chart, trend line, equation on chart, number 0.00089,305. So we are now going to do equals natural log of that divided by that over the natural log of that divided by that. And we get something that is, again, very close to 0. So we are now relatively convinced that it is half over order in BR2, first order in H2, and 0th order in the other 2. We can now put those answers in. Half order in BR2, first order in H2, 0th in N2, 0th in HBr. What's the rate coefficient for the reaction? So we now know the rate law. So remember that the rate law now is going to be R, and I'm going to put it in terms of the initial rate, is going to be Rk times our concentration of Br2 to the 1/2 times our concentration of H2 to the first. And these are, since we're looking at the initial rate, that's going to be our initial concentrations. Well, we know those concentrations, so we are going to take this expression. We are going to divide through, it's not letting me select what I want. Okay, and so now we have an expression for K. Simply going to be the initial rate divided by the square root of the BR2 concentration and the concentration of the H2. So our rate coefficients are going to equal our initial rate divided by, open parentheses, our BR2 concentration to the 0.5 times our H2 concentration. We can copy that over. And we see that they are relatively consistent. So why not average them? 29.3. So here we say it is 29.3. Now, what are the units of this? Well, let's take a look at our rate law. Well, we know the rate on the left-hand side has to be in rates of molarity per second. We know that H2 is going to be in units of molarity. We know that the square root of BR2 is going to be in units of molarity to the 1/2. So if we divide through by that, we end up with K being in units of molarity to the negative 1/2 seconds to the -1. Molarity to the negative 1/2 seconds to the -1. Taking data at 600 and 700, find the activation energy for the reaction. Okay, so we need to take 2 more data points. So we'll come over here, 0th order in that, so we don't really need to worry about it. I'm going to leave the N2 there for the moment, so we're at our initial conditions, but we want to take this data now at 600 degrees and then at 700 degrees. There we go. X comma Y, copy, come back over here. I'm going to come over here and paste numeric. I'm going to find our initial rate. Let's first take a quick look. Yep, early curve, so we're going to skip the first few data points. So we'll come down to here, do something like that, search scatter. We're going to now add a trend line. Equation on chart. Display it as numbers. There we go. All right, so bring this back. So we're going to have now 0.00026,119 for an initial rate. We have the same concentrations that we had here. Come on, select, copy, paste. I put that in the wrong place, so I'm going to move it right here. And we can, but the reaction orders won't have changed. So our K expression here is going to be the same as that. Okay, so we now have, I don't know why that one's screwed up. That's interesting. Must have hit something wrong. All right. Okay, so that's our average for 650K. So I'm going to put that right here, 650, excuse me, degrees C. This is our 600 degrees C. We now want to do 700 degrees C so that we have a third data point. So coming back over here, we change this to 700. X comma Y, copy, over here. Over that. Paste numeric. Conditions are the same. Looks pretty good. Let's skip the first 3 data points. So down to about there. Insert chart, trend line, equation on chart. Let's give ourselves some more digits. And we have 0.00266366. All right. So we now have 3 data points for our Arrhenius plot. So I'm going to put them up here. We have the temperature of 600, 650, and 700. And we have our rate constants. This one is going to equal, we need to copy that over here. Now, the rate constant for 600 is that. Our rate constant for 650 is that. Our rate constant for 700 is that. Now, what is an Arrhenius plot in order to determine the activation energy? K equals A e to the minus EA over RT, which means natural log of K equals natural log of A minus EA over R times 1 over T. So if we plot natural log of K versus 1 over T, where T is in Kelvin, our slope is negative EA over R. So we need natural log of K. Actually, we're going to do 1 over T first, and we're going to do natural log of K second. So equals 1 divided by, open parentheses, converting to Kelvin, 273.15, plus our temperature, close parentheses, enter. We copy that formula down here. We have them all done. This equals the natural log of K. Copy that down here. And now make a plot of this, scatter. We then put a trend line on, and we give ourselves the equation, and we have our slope is negative 19745. This is in units of Kelvin. Now, we need a value of R. We can look that up, 8.3145. I've got too many decimal points. In units of joules per mole Kelvin. So if our slope equals negative EA over R, then EA equals negative slope times R. So EA equals negative slope times R. And that's going to be in units of joules per mole. We want it in kilojoules per mole, so in units of kilojoules per mole, we simply take this divided by 1,000. Our answer is 164. So we come in here, we say 164. Okay, we're done with the kinetics. Let's now move down to the questions we haven't done yet. So, question 14, does your pre-equilibrium approximation rate law match the rate law you determined through your simulations? So let's take a look at what rate law we determined experimentally. R equals K, concentration of Br2 to to the 1/2 times concentration of H2. So R experimental. Our R pre-equilibrium expression was this one. R pre-equilibrium equals that. And just so that we can make this a little easier to see, I'm going to take it out of this notation. So anything with a negative, I'm going to move to the bottom. X, V, there. And then this. Okay. And so let's compare these two. The H2 order is correct, but the BR2 is not, and the HBr is not. So no, because the orders with respect to HBr and BR2 are incorrect. Okay, question 17. It's a lot of algebra to get from the steady state things that we had to this expression, but we do it. Okay, so we get to this point. Based on that expression, are there conditions under which this rate law is consistent with the experimental rate law, this one? So if we look at this, the numerator looks just like this. We've got BR2 to the 1/2 and H2 that is to the first. So in the denominator, we have two regimes. One regime is that the first term is larger than the second term, in which case the BR2 is going to end up going up into the numerator, and we're going to have a rate law that looks just like the pre-equilibrium approximation. And so it's not going to work under those conditions. But if this first term is small compared to the 1, then this just becomes the numerator. So based on this expression, are there conditions under which the rate law is consistent with the rate law you determined from your situations? Yes, if this is small. So what's necessary for that to be small? If K4 times HBr is much less than K3 times BR2. So that one. What experimental test would you perform to validate this mechanism? Okay, well, what we would want to do is make it so that this term in the denominator is much higher than 1, and so then the reaction orders would change in this particular way. So what we would want to do, how do we make this bigger experimentally? Well, we flood the system with lots and lots and lots of HBr. Flood the system with HBr. And we are done with the exam.